Welcome to topic B4, Newton's laws and examples. We're going to start by reviewing some of the things that we've learned in Unit 2 forces, and then we're going to learn about Newton's third law and apply all of this to some examples. So let's review what we know first. We know that force is a push or a pull on an object. They may result in acceleration. A force is a vector quantity that has magnitude and direction. And that's why when we write the letter for force, capital F has a vector arrow on top of it. We've learned there are many types of forces that we'll deal with this year. With the exception of gravity, all forces are contact forces, meaning that two objects must touch in order for the force to occur, and the object does not actually have to be touching the earth because the force of gravity is a non-contact force. When we're starting problems in Unit 2 forces, you always want to start with a system diagram, which is a sketch of all the objects, and it will help you label your givens. And then you're going to work on a free body diagram, isolating one object and all the forces acting on that object. There are some rules that you have to follow, some conventions for a free body diagram or FBD. It's only one object that represents the dot or the box, or you can draw a system as the object. And all the external forces will be shown on that object and labeled. They will all be going outwards. The combination of all the different types of forces on an object can be balanced, and then the object is not accelerating. An object is not accelerating if the object is at rest or traveling at a constant velocity. The combination of all of the forces might be unbalanced, and there's an overall force causing an object to accelerate, which means changing velocity. We can combine all of the forces on an object into something called the net force. And the symbol is F net or sigma F with, of course, the vector arrow on it. We find the net force by adding up the individual forces on that object. You can think of it as like a total or overall force, and it will help us see whether there is balance or unbalance. In many problems, you'll need to do the X component of net force or the Y component of net force in order to solve. We've also learned more details about specific forces. We've learned that the force of gravity is mass times G, which is 9.81. We've also learned that the normal force, in many cases in grade 11, will just be equal to the force of gravity. So vertically, if there is balance, the normal force will equal the force of gravity if it's a horizontal surface and there's no additional applied force. So these are all review concepts that we've covered so far. We've also talked about Newton's first law, which is also known as the law of inertia. If the net external force of an object is 0, the object will remain at rest or continue to move at a constant velocity. And there are 3 implications for Newton's first law. Objects at rest will remain at rest, objects in motion will remain in motion, and external forces are required to change speed or direction. And that's for Newton's first law. It's also known as the law of inertia. Inertia is the property of matter that causes it to resist changes in motion, and it's directly proportional to an object's mass. So if you look at this picture, who would be easier to move and why? So if they are starting at rest, the little guy on the right will be easier to set in motion. Less mass equals less resistance to changing motion. So that's what we mean by directly proportional to an object's mass. We've also gone over Newton's second law, but just to recap, this states that if an external net force acts on an object, the object will accelerate in the direction of the net force. And also the magnitude of the acceleration is directly proportional to the magnitude of the net force and inversely proportional to mass. If we take a look at this smart car and big bus, at a red light, which one has more get up and go? The smart car is obviously easier to start accelerating with a certain force. If you're at a green light and the light suddenly turns red, which one is easier to come to a safe stop? With a set amount of force, it would be much easier for the smart car to do that. So less mass is less resistance to changing motion. And we've graphed these relationships as well. Newton's second law can be turned into a mathematical formula that we use all the time, F net equals ma. Remember that we can apply F equals ma alongside the kinematic equations because the acceleration of the kinematic equations is connected to the acceleration of Newton's second law equation. Let's do an example. A 0.5 kilogram cart is placed on a table attached to a 0.2 kilogram weight, as shown in the diagram. Calculate the acceleration and the force of tension. We have a cart and pulley problem. And in this problem, since we have two objects, we're going to be creating two free body diagrams and solving a linear system of equations. So that's how this example is a little bit more challenging than previous examples. You can find this example on page 16 from the student notes package. And you're going to start this problem like any problem with a system diagram, and you're going to label the givens. So if we reread the problem, we can see that the first cart, the cart on the top of the table with the wheels, is 0.8 kilograms. And the hanging mass is 0.2 kilograms. We've labeled our system diagram. Now let's talk about some assumptions that we're going to make in this type of problem. The first assumption is that the string has no mass and it doesn't break or stretch. And the last assumption we're going to make in this particular example is that there's no friction on the pulley or between the table and the rolling cart. Number 3 is an assumption that we won't always be able to make in this course, but number 1 and 2, you can make these assumptions without stating them. So we're going to start by drawing a free body diagram for the first object. For this object, since it has mass and it's resting on a surface, not sinking into the surface, we have Fn and Fg, and they should be equal size vectors. Then we also have the force of tension to the right. That would be the reason why this cart moves at all. Since we don't have any friction, there's no force to balance out in the left to prevent this object from accelerating to the right. So whenever you have a problem in this unit, after you draw your system diagram and there's more than one object, you want to identify the direction of motion if there is motion. So if forces are not balanced, what will be the direction of motion? So you can see over to the right and down, depending on where you are in this string. So for the free body diagram, which is the first step that we always do in this unit, after drawing the diagram with the givens, we'd write our F-net statement. And the F-net statement in this case is Ft. We also know Newton's second law applies here because if it moves, there's acceleration to the right, which is the same direction as the net force. F-net equals ma. Since both of these two things equal F-net, we can set them equal to each other. Ft equals ma. And you want to ask, what am I solving for? And am I getting closer to solving? Even though in all of these problems, we start with the system diagram, the free body diagram, and our FNet statements. Are we getting closer to solving the problem? It asks for the acceleration of the cart. So I am getting closer to solving the problem because I started out with statements that didn't have the acceleration that I'm trying to solve for. And I can see the acceleration is now visible. We have mass. We don't have the tension force. But since we have these two assumptions that the string doesn't break or stretch, what that means is the tension here is the same as the tension here. Since the string does not stretch, the tension is even. And we can actually draw a free body diagram for this object now. Since we reached a dead end with the green free body diagram, we can't go any further to solve for acceleration unless we had tension. Drawing the free body diagram for the hanging object, we know we have a force of gravity. This will be Fg2, whereas this was Fg1. The Fg2 is smaller than Fg1 because it's smaller mass. We know there's also upwards tension, but I want to think about what's happening in the problem to draw an arrow that reflects relative size. So I want you to pause this video right now and think, is my upwards force of tension here going to be bigger or smaller than the force of gravity on the hanging object? So the answer is the force of gravity should be, the force of tension should be smaller than the force of gravity. So I'm just going to exaggerate that here and state it explicitly to remind myself that the force of tension is going to be smaller than the gravitational force downwards. The downwards force is bigger than the upwards force because I know my acceleration is down. For the same reason I know my acceleration is over. Over and down is the acceleration. Like we did with the first free body diagram, we're going to write the FNet statement based on this free body diagram, which is Fg2 minus Ft. Apply Newton's second law, Fnet equals ma, but we are going to have to write m2a to differentiate that it's different than our first mass. This was mass 1, and this is mass 2. I can see these are two statements for the net force on object 2. Therefore, they are equal to each other. m2a equals Fg2, which is equal to m2g, minus Ft. So Ft equals mg just based on our equation for Fg with objects that are near Earth's surface. On this side, can this equation be used to solve for acceleration? We do have mass 2, we do have g, which is the constant 9.81, we still don't have Ft. But because of the assumptions that we've made, the accelerations will be the same and the tensions will be the same. So we have two equations and it's the two same unknowns. So if we call this equation 1, we can sub equation 1 into equation 2. This is like you did in grade 10 math when you were solving linear systems. Substitution of m1a into the place of Ft. So let's rewrite equation 2, m2a equals m2g minus, then we're going to substitute what Ft is also equal to. Ft is also equal to m1a, so we are combining the information from the two free body diagrams into an equation which has all values that are known or that we're trying to find. So m2a plus m1a equals m2g. The m1a term becomes positive because we bring it to the other side. The a terms are collected. Now we can factor out a. Addition is commutative, so it doesn't matter if it's M2 plus M1 or M1 plus M2. Then the final step to isolate A would be dividing both sides by M1 plus M2. Substituting our numbers in. And using our calculator, we can find that the acceleration is 1.962 meters per second squared. That acceleration applies to the acceleration to the right of object 1 and the acceleration down of object 2, since they're connected by the string. When object 1 moves over 10 centimeters in a certain amount of time, the hanging object moves down 10 centimeters in the same amount of time. Acceleration is equal to 2.0 meters per second squared over and down. We want to round to two significant figures because in the original question, the masses were given as 0.80, 2 sig figs, 0.20, that's 2 sig figs as well, and we always round our final answers to the smallest number of sig figs out of the numbers that we've used. So that is the question. Calculate the acceleration of the cart. There's also a second part that asks for the force of tension. When you're solving these problems where you have two objects, you have two equations, and you had to solve the system of equations, there are two unknowns that you can be asked to solve for. Ft equals m1a was known from equation 1, so solving a took quite a bit of work, but solving ft is one line because we're going to rely on our calculated value for a. Remember that if you ever have to carry forward a number, you want to carry forward the unrounded number because you don't want to carry forward error, or you don't want to amplify error by rounding too early. And then for our tension, we get 1.5696 newtons, and rounding to two significant figures would be 1.6 newtons. The question actually asked for magnitudes of these values, but force of tension is a vector quantity, so I am going to report it with a direction. It never hurts to report it with a direction. If it's not requested, it just helps you double check the problem. The force of tension direction is upwards if you're talking about object 2, or it's over to the right if you're talking about object 1. So that's how we would complete this question. Sometimes this question asks you for acceleration and force of tension together, and sometimes you just have to know that you have a system of equations since you have two objects and a linear system of equations. Now the next step, if this was really easy, what you should ask yourself is, how can we do this problem if we add friction? So I want you to pause this video and ask yourself, what might change if I added friction into this problem? Okay, in this problem, we did not consider friction. You might guess that the acceleration will be lower if you do have friction between the table and the cart. And we're going to try that problem in a few days. So now that we've done a pretty challenging problem that incorporates a lot of different concepts up until now, up to Newton's second law, let's talk about Newton's third law. And the nickname of Newton's third law is the action-reaction law. And if you're following along with our student notes package, it's on page 17. Newton's third law states that if object A exerts a force on object B, then object B exerts a force on object A that is equal in magnitude but opposite in direction. Mathematically, we can say F of A on B equals negative F of B on A. There are 3 examples of action-reaction pairs. Fish fins push water backwards, and the water pushes the fish forwards. So this is an action-reaction pair. The force of the fins in the water could be considered the action. The force of the water forwards on the fins could be considered the reaction. They're the same size and opposite direction. Another example, it's similar. It's how birds fly. So birds fly using their wings, and their wings push down on air, and the air pushes up on the bird. Mathematically, the force of the wings on the air equals negative force of air on wings. Another example, you've got Yoshi pushing this box to the left. The action force might be considered the force of Yoshi on the box, and the reaction force is the pushback of the box on Yoshi. So maybe if there was a pattern on this box, if there was an imprint, Yoshi would have the imprint on his skin when he releases, and that's evidence that there's a reaction force. One important thing to note is that the action and reaction pair of forces are the same type of forces, and also that they always act on different objects. So notice how the force here is on the box, the reaction force here is on Yoshi. And so on the box versus on Yoshi. This force, this action force, would have to be on the free body diagram of the box, since the free body diagram includes all the forces that are on that object. The reaction force is on Yoshi, so that would appear on the free body diagram on Yoshi. An action-reaction pair of forces can never appear on the same object or on the same free body diagram. So let us try some examples. I'll give you a moment to read. While driving down the road, a dragonfly strikes the windshield of a bus and makes a mess in front of the face of the driver. This is a clear case of Newton's third law of motion. The dragonfly hit the bus and the bus hit the dragonfly. Which of the 2 forces was greater, the force on the dragonfly or the force on the bus? Let's pause and think. If you said that the forces are equal, you're correct. Because of Newton's third law, this action-reaction pair of forces have the same magnitude. The impact of that force is more obvious on the bug because the bug has a very small mass, and mass is inversely proportional to deceleration. So the bug has a very small mass, therefore big deceleration. So the common answer is that the force on the bug is greater, but that's incorrect. It's Newton's third law, the forces are equal. Okay, let's try another example. Many people are familiar with the fact that a rifle recoils when fired. This recoil is a result of action-reaction force pairs. A gunpowder explosion creates hot gases that expand outward, allowing the rifle to push forwards on the bullet. So that might be the action force. Consistent with Newton's third law of motion, the bullet pushes backwards on the rifle. The acceleration of the recoiling rifle is A, greater than that of the bullet, B, smaller than the acceleration of the bullet, or C, the same size as the acceleration of the bullet. So pause this video and make your best guess. If you guessed that the answer is that the acceleration of the rifle is smaller than the acceleration of the bullet, that's correct. If we take a look at the mathematical statement of Newton's third law, and then we substitute Newton's second law, F equals ma, if it's the only force on the bullet. If the force of the rifle on the bullet is the only force, then it is the net force, which is equal to ma. So mass of the bullet times acceleration of the bullet equals the mass of the rifle times the acceleration of the rifle. Since the mass of the bullet is very small, the acceleration of the bullet is very large. And so if the mass of the rifle is much bigger, then the acceleration of the rifle is much smaller. So that's why the answer is B. Let's try another example. So Newton has a mass of 73 kilograms and the elephant has a mass of 5,000 kilograms. They push on one another with a force of 100 newtons while standing on skateboards, which make friction negligible. Negligible means it's too small to need to take into consideration in the problem, so it means you can ignore it. Draw a free body diagram for each and calculate their acceleration. So here's Newton and the elephant. Okay, so taking a moment to draw the free body diagram. We have force of gravity for both, obviously different magnitudes, normal force for both. We have the action force pushing the elephant to the right, according to this diagram, and we have the reaction force pushing Newton to the left. The magnitude of the action and reaction forces are equal. If we know that the action force is the only force acting on the elephant, that's the net force, and net force is also equal to ma. Same thing for Newton. So we end up getting acceleration is equal to the reaction force divided by mass, or for the elephant, acceleration is equal to the action force divided by mass. Now you might argue that maybe the action force is actually the action on Newton. Who started the fight, the elephant or Newton? Who knows? So the designation of action or reaction, it doesn't really matter which one you call action, which one you call reaction. Noting that you're dividing by a much bigger mass, you get a much smaller acceleration for the acceleration of the elephant. Okay, now let's do some of the problems that put all of Newton's laws together. Here are some tips. So often the problems that combine Newton's laws look like one of the following. Either where you're applying Newton's laws and those kinematic equations, and the thing that connects unit 2 with unit 1 is acceleration, pulley problems, or multi-body problems. So here are some of the tools. This is just a reminder, sort of a review slide of everything so far, that when we're solving problems, you want to think of what tools we have available. You're always going to want to start with the tool that is your free body diagram to identify all the forces and summarize all those forces with a net force statement. We've got Newton's first law that applies to objects that are at rest or at constant velocity, traveling at constant velocity. Newton's second law applies, F net equals ma, if we don't have F net equals 0. So if the forces do not balance, then the net force is equal to mass times acceleration. We also know Newton's third law, action reaction, and the kinematic equations. So these are the tools that we have. So you can pause this video at any time if you need some of the blanks for the note on page 19 of the student notes package. So you can always come back to these 5 tools in order to solve the problem. And you want to think of whether you need these tools in this order. When you combine the laws together, you might get pulley problems. In pulley problems, just a reminder that tension is a pulling force exerted by a rope or a string. We can assume that the rope doesn't stretch or break, it's massless, and the pulley is also frictionless, unless otherwise stated. So if we take a look at the free body diagrams for a few different pulley problems, so pause the video right now and try and create free body diagrams for everything you see. Just a reminder that a free body diagram is focusing on one object. So since the first diagram has two objects, or each diagram has two objects, we'll have two free body diagrams for each. So pause the video right now and see if you can draw them out. It's really important that you label them. So this is object 1 and this is object 2. So you'd have FNet 1, free body diagram 1, free body diagram 2. Okay, taking a look at our answers. For the pulley problem, we have mass 1 that has a bigger force of tension than force of gravity. Mass 2, which is a bigger force of gravity than force of tension. How do we know that? Assuming that the size of this shape indicates that the mass 2 is bigger than mass 1, when we let go, this pulley will rotate clockwise. So mass 2 will fall down, will accelerate down. So acceleration is down, that means net force is down, so Fg is bigger than Ft for mass 2. If we do a free body diagram for this problem on the desk, you will have Fg and Fn equal to each other because the object isn't sinking into the desk. And Ft will be included for sure. Ff will be included if you want to consider friction, but Ft will be bigger than or equal to Ff. For this hanging object, if there's not enough friction to balance out this object, then Fg will be bigger than Ft. If friction was big enough, then Ft and Fg of mass 2 will be equal. I'm going to just leave you this third diagram as food for thought. It's something that we do in grade 12. So these problems are longer problems that might be intimidating at first, but we want to think of the tips, our steps and tips that we've been using so far for these longer problems. We've always drawn a free body diagram for each mass. Then we write net force statements for every free body diagram. And you're going to pick which net force statements are the most useful and write them using Newton's second law, and then make any substitutions necessary to try and connect what is given with what is required. So for example, you might have to substitute Fg equals mg. You might have to substitute a Newton's value for friction, or coming up soon, we're going to have an equation for friction. You might have to sub in Newton's third law that F action equals F reaction. And we might use a substitution step to solve for the required information. One of these types of problems where we're going to apply these steps, other than pulley problems, is called multi-body problems. And that occurs when a single applied force causes multiple interacting objects to move. The single applied force could be a pushing force or a pulling force. Some important things to note. The applied force only acts on one block. The acceleration of all blocks is the same, and there are action-reaction pairs in between the interacting blocks. So let's try this problem, and this is our last pretty challenging problem that will help you with your practice problem that you're going to do today. Where we have three objects connected by strings and there's a pulling force. So this is a multi-body problem because there's a single applied force that causes multiple interacting objects to move. Our 9.4 newtons is only being applied to the first box here. We notice we have three objects. That means we could draw a free body diagram for each object. In this example, I'm going to show you that we can actually draw a fourth free body diagram for the three objects together. So we can do sort of a total mass and do the free body diagram for the total mass, and that might help us in this problem. In this question, we're asked for the acceleration of the blocks. Notice it doesn't ask for the acceleration of the first block or the second or the third, because all of the accelerations are together. We do have the assumption that there's no stretch in these ropes. And I tried to draw one as a chain and one as a rope just to emphasize the fact that they are different tensions. So we're going to call this one FT1 and this one FT2 if we have to solve for those. We're also noting there's no mention of friction, so we're going to assume that there is no friction between the surface and the objects. The question is, what is the acceleration of the blocks? We know F net equals MA, so we know we need an F net statement, so we'll need a free body diagram to base the F net statement on. If we use the free body diagrams of all three objects together, so we're going to combine all three objects together. It's going to be mass total that we're talking about accelerating this way. We only have the 9.4 newtons force horizontally. We of course have the FG total downwards and the FN total, the normal force upwards. If we combine these three objects together, the free body diagram is very simplified. There's fewer forces than if we had to deal with all of these action-reaction pairs. So for part A, let's combine all of the objects together to calculate acceleration. We know that net force is equal to total mass times acceleration. We can solve for acceleration because we know net force and we know total mass. Now we haven't explicitly stated them, so let's write those in. F net is equal to FT, F applied, which is 9.4 newtons. So that's given, that's a given. Do we know M total? It's as simple as adding up the masses. 3.2 kilograms plus 4.4 kilograms plus 1.8 kilograms gives us 9.4 kilograms M total. So we have mass total and we have F net if we were talking about the net force of the three objects combined. So 9.4 newtons divided by 9.4 kilograms gives us an acceleration of 1.0 meters per second squared to the right. Acceleration is a vector, so we're going to include that direction. The smallest number of sig figs out of the numbers we used was 2 sig figs, so we're going to round to 1.0. Even though on our calculator it tells us exactly what. Part B is a little bit trickier. It asks for the magnitude of the force between M1 and M2, or M2 and M3. This was object 1, object 2, object 3. So we want to know that force in between. So for the object 1, it would be a force to the left. For object 2, it would be force to the right. We have options for B and C for which free body diagrams we would, diagrams we would use. So as we already know acceleration, that's one less thing we have to calculate. Finding forces in between two objects, whether it's a pushing or a pulling problem, it's always easiest to work with the FBDs of the outer objects and then move inside to the middle if you need to. So object number 3 is the 3.2 kilograms force, 3.2 kilograms object. It has a force of tension to the right, force of gravity down, normal force up. There's nothing on this side, so this is the simplest free body diagram to use to solve for an internal force. This is the force of tension 2, which is the force of tension between objects 2 and 3. The net force for this object is mass 3 times acceleration. We also know net force is equal to the force of tension that we are trying to solve for. For the force of tension we're trying to solve for, it's M3 times A. M3 is 3.2 kilograms, and acceleration we've already solved for. Make sure if this was a calculated number that wasn't so wasn't an exact number. Make sure you're using the unrounded number to carry forward. So we get 3.2 newtons to the right if we're solving for it using object 3. And part C is asking for the other force of tension. It is recommended that you rely on the fewest number of calculated numbers. If we don't have to rely on any calculated number, that would be great. We are going to rely on this calculated acceleration. But if we drew the free body diagram for the middle object, we will be using calculated values both directions, both the calculated FT2 and the calculated acceleration. So we're going to take the object at the end, object 1, and draw the free body diagram for it. We have the 9.4 newtons force to the right, and we have a smaller FT1 force to the left. FG1, FN1 would be the forces for it to be a complete free body diagram for full marks. Notice that 9.4 newtons force is bigger than FT1 because I do know I accelerate to the right. So that's how I know 9.4 newtons has to be bigger than FT1. F net equals M1A. F net also equals 9.4 newtons minus FT1. I'm trying to solve for FT1, so I'm going to set this equal to that. M1A equals 9.4 newtons, subtract FT1. And now I simply rearrange for FT1, 9.4 newtons minus M1A. So we substitute our numbers for that new equation we derived based on the free body diagram of object 1, and we get 7.6 newtons. Just taking a look at our answers and doing a common sense check. So does it make sense that tension here is bigger than tension here? So pause your answer and do the common sense check for my solution. So if you said yes, you're right. There is more tension here than here. So if you were given 2 different ropes, you want the stronger rope to be here because it's carrying more mass. And that's example 8 from page 23 in the student notes pack. Okay, since now we've reviewed all of Newton's laws and learned Newton's third law and done several long answer examples that combine them together, now it's time for you to practice. So complete these practice problems and submit them to the Google Classroom. Don't forget to submit what's requested to Google Classroom for the task called B4, which if you didn't read it in the week at a glance, the tasks, we will be numbering tasks instead of calling them lessons. Unit 2 will all start with B, and this is the 4th chunk or task of Unit 2 forces. Have a great day.